Hi, Madhu.
Hi, how are you?
I'm good. Yeah. So you're able to hear me clearly?
Yes, I can.
Very good. So maybe so it starts in about 5 minutes from now.
Okay,
So maybe you can try to upload the slides and see everything is fine or not.
sure.
Yep.
It's
That's pretty
visible,
good.
right?
Yes.
Okay, sounds good.
Can you just do some slide changes and let's just yeah, it's good. Great.
Nice.
So let's just wait for next few minutes and we'll just start.
Sure.
So your son is good now?
Yeah, yes. It's just timing of these things.
Right. let us wait for another minute, then we'll get started. Okay, so maybe we can get started. More people will join in during the presentation. So, yeah. So let me welcome everybody to this ECU webinar. And many thanks to Professor Madhu Bhaskaran for agreeing to give a talk in this webinar series. So Professor Bhaskaran co-leads the Functional Materials and Microsystems Research Group at RMIT University in Australia. So she has won several awards and fellowships for her research, including medals from leading Australian academies. And she was also named as Australia's most innovative engineers by Engineers Australia, and as well as she was on the MIT Technology Review Top 10 Technology Innovators under 35 in Asia. So her discoveries made at micro and nano scales, they have transformed into prototypes. They have been transformed into prototypes, and this has often been done with partnerships with industry. And her work seeks to transform conventional electronics, the hard electronics, into soft and unbreakable products. And so these are could be thin enough to create electronic skin. So today she would be talking about oxide-based wearable sensors for healthcare applications. Yeah. Madhu, welcome again, and all yours.
Thank you. Thank you very much for having me. And apologies, I had to cancel at the last minute last time. It was due to a health reason, but all good today. And thank you for inviting me to give you a presentation. So thank you for your kind introduction. And that pretty much covers everything on the first slide. This, in a snapshot, is what our group does. So the Functional Materials and Microsystems Research Group is now actually 11 years old. We established the group back in 2010. And it's essentially looking at materials at the micro and nano scale. And as you would all know, materials behave very differently at those kind of scales. And we use those properties for various applications. Even though my presentation today is more focused on stretchable and wearable sensors and conformal materials, our group is quite wide in the sense we work on quite a few different fields. So it's co-led by 3 different people. So I co-lead the group with Professor Sharath Sriram and Associate Professor Sumit Walia. So that allows us to actually work on quite a few different fields. But more interestingly, it also allows us to work at the intersection of these fields. So for instance, Sumit works a lot on ultra-thin 2D materials, and Sharath also leads a lot of the artificial brain memory devices. So we're also able to work at the confluence of these fields. So using 2D materials to mimic brain functionality, or using 2D materials and rendering them stretchable, or using the stretchable materials in combination with the brain mimicking electronics. So all these wonderful intersection research becomes possible as a result of this. Just few slides showing you the breadth of the work. So we work on quite a few different fields. As I mentioned earlier, some of the other work which we also do in the group include vacuum electronics. So this is essentially almost scaling down electronics and removing and making it operate in vacuum. So the idea is you get nano electronics which are capable of operating extremely fast because all you have is a vacuum channel between the source and the drain. This is work predominantly led by Sharath. So there are some papers in this area. If this is something of interest to you, do reach out to me and I'm happy to send you more papers in that field. Similarly, we've been working on terahertz devices for a really, really long time. We started work on terahertz devices back in 2012. So it's been nearly 9 years of working on terahertz devices. We predominantly bring in the fabrication and materials expertise in this case. We collaborate closely with University of Adelaide, who do a lot of the modeling, the simulation, and the testing of the devices. But when we started, this field was really, really young. I think there is still a lot of scope and opportunity in this particular field. But the main challenge in this particular field was the correct choice of materials, which provide low loss, and coming up with fabrication techniques which will allow you to etch many, many microns of silicon, or combining unique materials and able to get devices which are operating at low loss. So these are some of the devices which we have made over the last few years, and we have quite a few publications in this space as well. The third thing which we work quite a bit on is 2D materials. Now that is predominantly led by Associate Professor Sumit Walia. Mainly, we've been working a lot on phosphorine. So this again is work which has spanned over nearly 6 years now. It started off with trying to understand phosphorine, trying to understand why phosphorine degrades, coming up with mechanisms to protect phosphorine from degrading. But in the last couple of years, it's moved quite a bit into applications. So in terms of trying to use phosphorine for optoelectronics applications, or for even for artificial machine learning type applications. So this is again a space which is growing, and we have quite a few publications in this space as well. With that covered, I'll talk about this is the outline of essentially what I'm going to be talking about today. So as you can see, it's really, really oxide heavy. Oxides is something which I've done for a really long time. So we, in the group, we have nearly more than 15 years experience of working on oxide materials. Predominantly, they are sputtered. So a lot of sputtered oxides and a variety of oxides for various applications. So I'll be talking about how we use them for various electronic applications, for photonics applications, some of the industry-led projects which has allowed us to branch off into biomarker sensing using oxides. Some recent work where we're able to demonstrate electronic skin, so skin which actually kind of mimics the pain sensation in our skin. And towards the end, I'll talk to you a little bit about industry collaborations which are helping us commercialize some of our work and technology. So I'll start off with the conformal oxides, and this is which we started back in 2012. It started with a simple motivation. So we wanted to take oxides and render them stretchable and conformal. We realized there's a lot of interest, there's a lot of opportunity available in the wearable electronic space. And obviously, oxides are fantastic, versatile materials. But at that point in time, there was quite a lack of, trying to integrate oxides and trying to render them stretchable or conformal. Quite simply, there are quite a few challenges in doing that, mainly because oxide or functional materials are usually deposited at very high temperatures. And generally, oxides are extremely brittle. So, you don't really stretch them or flex them. You essentially end up getting cracks or something. And so they're not going to really work under levels of strain. On the other hand, you have stretchable materials which don't really withstand very high temperatures. So we wanted to see if we can come up with some kind of a process by which we can actually combine stretchable materials. So when I say stretchable materials, I mean materials like PDMS, which is silicone rubber, and use functional oxide materials and combine the two of them and use them for various applications. So what we essentially did at that point was we came up with a transfer process. This was kind of like a eureka moment. I don't think we planned this. It just so happened that, there was a mistake in the lab where we just forgot to add an adhesion layer, and that kind of led to a transfer process. So I guess that's lesson number one. Sometimes, wonderful things do happen from mistakes, or things which we miss sometimes can lead to wonderful discoveries. So the premise of this entire transfer process is the fact that platinum does not stick to silicon. So if you use platinum thin films on silicon, normally you use an adhesion layer like titanium or chromium or titanium dioxide. But in this case, we wanted to use that platinum as a transfer layer. So we put it down on silicon without that adhesion layer. Now, because you're still working on a silicon platform, what that allows you to do is you can deposit any oxide layer as you would do normally, and you can pattern it as you would do normally, heat it up as you require. So in this particular case, you have ITO, which is being deposited by electron beam evaporation. It's being annealed, at 400 degrees centigrade and also patterned using photolithography. So what you see in that image C over there is platinum sitting on top of silicon. Now we spin coat and cure the conformal stretchable polymer, PDMS, on top of this. And when you peel it off, what is essentially happening is because the platinum is not stuck very well to the silicon, the entire layer just comes off along with the oxide adhered onto the PDMS. So when you flip it, you have your PDMS, you have an oxide layer on top of it, and then you have the platinum sitting on top of it. You get rid of the platinum using an etching step, and you're left behind with your oxide kind of semi-embedded or kind of sitting half embedded on the PDMS substrate. And that's your way of transferring your oxide thin film or PDMS substrate. We were really happy with this. We thought we'll do a little more research. We'll understand, what are the parameters. We tried a few different thicknesses. We tried micro patterning them, nano patterning them using electron beam lithography. It worked every single time. So getting a large transfer rate over a very large area, like a 4-inch diameter silicon wafer, was possible every single time. And because the oxide is kind of semi-embedded inside the polymer, you have very high adhesion. So you don't have this flaking off or cracking off. It is pretty much set quite well within the polymer. We then thought, okay, we managed to do this. Now, let's see how this actually withstands some strain. So we strained this, and we were quite surprised to see that 3-4% is probably the max it might withstand, but we found it withstood up to almost 12%. And even if it became open circuit, once you again brought it back to 0% strain, it again recovered its original performance, and you could keep reusing it. So we were thinking, how did this happen? How is it possible that an oxide layer, which is usually quite brittle, able to withstand quite high levels of strain? And when we took a look at these materials in the microscope, we saw that it was no longer a thin film. So it's not that it's a thin film which has cracks. Now, normally, if you put gold metal films on PDMS, you will see you have just a cracked film at the end of it. This is not cracked. This is more of it's like a plate-like structure. So it's like overlapping plates sitting on top of each other. So when you look at this, you kind of realize what happens, because when you're applying strain, you have the plates moving apart from each other. But as long as the plates are making contact with each other, you're still having a functional device. Beyond a point, if you apply too much strain, plates kind of lose contact with each other. But then once you release it back, it can slide on top of each other again. So we kind of call this a microtectonic effect, because it kind of looks similar to the plates making up the geological crust. And we thought this is a unique thing which we got out of the transfer process. So not only did we manage to transfer it, we also managed to transfer it in such a shape and form that it's able to withstand some strain now. It's a fascinating transfer process because we did the usual thing. We sent it off to review to a journal, and the journal asked us the usual question of it works for IT or does it work for other materials. And we've tried quite a few different oxides along this journey now. So for instance, this image shows you the transfer process for zinc oxide. Exactly the same process using platinum as a transfer layer, except in this case, you're using zinc oxide. You can either transfer it as an entire thin film, as shown in this image E over here, or you can nano pattern it and then transfer it over, depending on your end application. They are quite versatile. So the fact that zinc oxide is a very versatile oxide that allows to demonstrate quite a few different applications. So what you can see in this particular case are gas sensors, which are capable of operating at room temperature, which is quite rare. And you can see zinc oxide is sensitive to both nitrogen dioxide and hydrogen. So, and with strain, you're not really using much of the performance. So that's a nice room temperature demonstration of gas sensing using these devices. And similarly, zinc oxide is quite sensitive to UV. So if you do a transmission spectra of zinc oxide, you'll find it's really sensitive in the UV region of the spectrum. And you can see over here, it's behaving in a very linear manner to UV exposure. So there's a change in resistance every time the UV light hits it, and then it recovers back to its original state. So the reason why these are actually behaving really, really well is we kind of attributed back to the fact that there's a microtectonic effect. So when you have a tectonic effect, what's essentially happening is the surface roughness of these materials are extremely high. So for instance, you have the zinc oxide sitting on PDMS. You can see a surface roughness value of around 160 nanometers in this case. That surface roughness, anyone who does sensors will tell you the higher the surface roughness, the better the sensing performance. And that is pretty much what you're seeing in this case. So really high surface roughness translating to very good sensing performance. be it in the form of gas sensors or be it in the form of UV sensors. So that was our work from back in 2015. And then because it was a very unique process, which allows you to do the process over quite a few different materials, we patented the process at that point. And we put out some media releases. There was a lot of industry interest at that point. And we thought this is a nice way to actually get something out into the market. It turned out to be quite a frustrating journey beyond that point because there were nearly 40, 50 different industry conversations which didn't effectively materialize into an industry collaboration for nearly 2 years. But I took every call. And I think I learned a lot from that process. So that's my tip, answer every email, take every call, because you never quite know what will come out of it. We spoke to a lot of industry partners globally in Australia, trying to see if there could be a way in which we could commercialize this particular work. There was some interest from defense because obviously these are gas sensors, so it's nice to imagine them in a wearable context for gas sensing applications. And also because they are good UV sensors, they are quite useful in the sense Australia has quite a high incidence of skin cancer. So trying to understand your UV exposure levels on a day-to-day basis is quite useful to have a UV sensor to do that. So those are some of the end applications which we had in mind when we spoke to quite a few industry partners. But as you can see, the materials are really thin and transparent, and we kind of achieved, what we set out to achieve, which was transparent, unbreakable electronics. I'll kind of leave that journey over there, and I'll kind of touch back to it at the end when I talk about some of the industry partnerships which we have. But the beauty of oxides is you don't need to restrict yourself to electronics applications. We use oxides quite a bit for photonics as well. So, for instance, we had the same transfer process, and we used titanium dioxide in this particular case to create tunable gratings. So if you look at titanium dioxide to PDMS, there's a very high refractive index contrast of 1.4 or 2.7. So this was a nice, very quick demonstration to show, one, that you can use the transfer process to create these kind of grating devices using titanium dioxide. And two, you can actually use mechanical strain to tune those gratings. So what you see in this particular case is the grating sample sitting in the middle. And as you see strain being applied on that sample, you're seeing a change in the diffraction patterns which you're observing from the grating. So using strain to actually tune these gratings is a novel possibility because of the fact you now have this sitting on a stretchable substrate. So similar kind of image over here, we went from -4% compressive strain all the way to 18% of strain, and you can see the way the material, the diffraction pattern of the grating is changing. We also did some finite element modeling in this case because we were trying to understand how you're able to go up to around 18 or sometimes even up to 25% of strain and not have any impact on the oxide material. So what you see in this case is the titanium dioxides are being modeled sitting in the PDMS platform. And when you apply strain, all the strain is actually absorbed by this PDMS layer. So you don't see the titanium dioxide is almost mechanically invisible. And that kind of explains why you're able to apply this much strain on these gratings and get away with it every single time. So the titanium dioxide sits in the middle of the PDMS, which absorbs all the strain being applied, and you're able to use these gratings again and again. Just some graph which shows you the measured strain and the applied strain. So you can kind of see how the experimental results using red light and green light match up with the analytical and the finite element modeling results. This was some of our early demonstrations. So our imagination then was this could be used potentially for strain mapping. And it's also a nice demonstration of a mechanically tunable application in photonics. But at the same time, we were also in collaboration with the University of Adelaide for our terahertz devices. We also worked with them for a bit on optical applications. So we did some dielectric resonators for them back then using titanium dioxide. And these which are seen over here are actually done on silicon. So we did some dielectric low loss devices because titanium dioxide is a low loss material. And we were able to actually demonstrate some nice devices on silicon. The fact that we could now a platform where we could transfer these dielectric resonators onto a stretchable platform got them really excited. So they asked us, can you make meta surfaces? So trying to make these meta surfaces is quite nice because usually meta surfaces were made using metal. Now metal is a highly lossy material, so it's not really efficient to use it for meta surface applications sometimes. And the fact that it's on PDMS also lends the tunability. So the fact that you can now stretch it and tune the meta-surfaces is an interesting application for the entire concept. So they designed these to actually work in the visible wavelengths. So what you essentially have is disks of titanium dioxide sitting within a PDMS platform. These are some of the simulation results they gave us. So what you see over here is you change the polarization of the light, and based on the amount of strain which is being applied on the sample, you are red shifting or green shifting the resonance of the sample. So as you can see over here, it's with bipolarized excitation. You can see the resonance shifting with application of strain. And in this particular case, it's green shifted with the application of strain. These were the simulated results which they sent us. And this was the equivalent experimental results which we obtained back then. So nice demonstration again to kind of show flat devices for the future, where everything is no longer need curved optics, which is usually what really adds to a dimension of optical devices. And it's a nice demonstration where you also show the mechanical tunability concepts in it. We didn't quite work too much on optical devices after that for quite a long time, but this new ARC Center of Excellence has kind of given us the opportunity to further this. So this is a brand new Center of Excellence. So to explain a little bit about Centers of Excellence, they are an Australia-wide Australian Research Council awarded center. So this particular center was funded at $35 million from the Australian Research Council. There are 5 organizations involved in this, and it's a 7-year program. So the idea behind this is to bring people together to solve big problems. So in this particular case, it is to create transformative meta-optical systems. That's why we're called TMOS, to basically create the next generation of optical devices. For TMOS, we're looking at generating light at the nanoscale, manipulating light at the nanoscale, and light at the nanoscale. So that's the 7-year goal, to have the to actually generate, manipulate, and detect light at the nanoscale. A lot of our work essentially sits in the manipulate theme. So using various forms of either tunable mechanisms to actually manipulate light and therefore have interesting concepts. You can check the website, so tmos.org.au. We are recruiting some PhD candidates and postdocs. The pandemic has kind of set us back in that sense in terms of recruiting the PhD candidates, but there are some ads right now for postdoc positions, so do have a look. Some of the other materials which we work on, which also fit quite well in the TMOS context, is phase change oxides. So vanadium dioxide is a fascinating material. There's been a lot of interest in vanadium dioxide in the last few years. As a concept, it's quite a controversial concept. People quite don't agree on how it fundamentally behaves or works that way, but we just find it a fascinating material. So it's a material which actually changes phase from being an insulator at room temperature to becoming a conductor once you heat it up to around 70 degrees centigrade, and then switches back to being an insulator once you cool it down. The fascinating thing with this material is it not just changes its electrical properties, it also changes its optical characteristics with heat. So you can see over here, the optical characteristics in the IR region of the spectrum is quite different when you heat up the sample from 30 to 90 degrees centigrade. So we did some work in this particular space where we managed to develop a substrate-independent recipe. Until then, a lot of the vanadium dioxide was deposited on sapphire or lithium niobate or really expensive substrates. We managed to get this working on glass, on silicon, on most standard substrates. So that allows for easy integration into electronic or optical devices. So it's a fascinating multi-stimuli material. So you can excite this using light. So using photo excitation, you can excite electrical impulses, or you can excite it thermally by heating it up. So some of our recent work in this case was when we tried applying different stimuli on the material to try and understand how the photoresponse of the material actually changes once you apply 3 different kinds of stimuli. So this kind of shows you the mechanism of what happens where you have deep level, where you create some intermediate states, and that affects its photoresponse generation occurring at different wavelengths. So you can see in this particular case, we measured the photoresponse across different wavelengths at room temperature, which changes significantly once you heat up the material to 65 degrees centigrade. So 65 degrees centigrade is when it's actually transforming from being an insulator to a conductor. So it starts behaving very differently once you heat up the material. So this recent paper, which we published last year, kind of shows you how the material behaves differently, how the photoresponse of the material actually changes once you heat it up, and how there's a wavelength dependence to that photoresponse measurements. All right. So I'll kind of move away from electronics and photonics and kind of go a little more towards oxides for biomarker sensing now. Um, Now, this is a very different kind of a project because this was not something which we thought about ourselves. A lot of the ideas which we have basically comes from us going, okay, why not? Why don't we do this? Why don't we do that? This kind of came as an ask from industry. So this was not something which we organically worked on, but because industry asked us for a solution to their problem, this kind of set us off along this journey. So what they essentially wanted was we have a lot of biomarkers in our body, and the ability to actually sense these biomarkers without a blood test was basically the ask. So we don't have to have a blood test to detect the presence of these biomarkers. The same biomarkers which are present in blood are also present in saliva, are also present in sweat or in tears. So how do you actually analyze other body fluids? And can we get a quick analysis of our body fluids to understand the presence of various biomarkers in the body? That was the ask from industry. So put simply, a sensor which somebody can use very simply by themselves without having to have to go to the doctor and understand their health condition. So we thought, fine, let's just maybe go back to our oxides and see if they allow us to develop a biomarker sensor. A lot of the approaches which we take are usually conductometric. So what we're looking for is a change in the electronic properties of the oxide, which we usually measure. So we went almost exactly with the same kind of an approach. We started off with zinc oxide, which we silanized in this case to make it more hydrophilic. And then we attached the antibody on top of this. And essentially then the last step, so is then you attach onto the antigen and you have a charge transfer happening as a result of the antigen binding onto the antibody, which you measure off as a change in the conductometric properties of the oxide. So as a product, if you think about it, this is what you would sell. You'll sell an antibody immobilized device, which has a particular resistance in the market. When you go and you use this as sample, so say you add a saliva sample on top of this, the presence of the antigens, they attach themselves to the antibodies. You have a change in the resistance, which you measure, which is indicative of the amount of the antigen which is present. And possibly you could reuse these devices, which is what we're trying to test now. It's quite a fascinating concept because of the fact that you can use it quite sensitively on a wide variety of biomarkers. So these are some of our interesting examples where we studied IL-6 and CRP. Now, IL-6 is interleukin-6 and CRP is C-reactive protein. These are important biomarkers in our body which are indicative of cardiovascular diseases. So if you look at this, there are healthy levels of IL-6 which are present in sweat or in saliva. And this sensor is actually capable of picking up the concentration of IL-6 well above and well below the healthy levels. And similarly for CRP, you again have the sensitivity, which is beautifully demonstrated on either side of the healthy levels in sweat or in saliva. But selectivity is also key for sensors. So if you have a mixture of everything and you have an IL-6 made sensor, as you can see, this particular one on the left-hand side is an IL-6 sensor, which records the maximum response for IL-6. The one on the right, the CRP, and is responding only to CRP as opposed to all the other biomarkers which might also be present in our body fluids. I'll kind of touch back again on this towards the end to kind of tell you about how then led to, how that led to industry collaborations and what you can actually use this platform for in practical sense. The final concept in terms of oxides, one of the recent work which we did was using oxides for electronic skin. This was right from the beginning. We always talked about electronic skin or e-skin or using materials which are very similar to skin. That was using PDMS because PDMS has properties which are very, very similar to skin in mimicking the skin. So this was where we kind of brought together 3 different concepts in the group and we kind of demonstrated a pain mimicking skin, electronic skin. I spoke to you a little bit about the brain mimicking electronics earlier. So a lot of work was done for the last 5 or 6 years in the group, where we again used oxide memories or memristor devices. There's a wide history or the background literature to this, so please do go read up about it. But essentially what you're using is resistant states to store information. So these are kind of resistive memories. So they are resistors whose performance depends on the previous voltage cycle that they have seen. So in some ways, they are fascinating because they behave very similar to our brain. So if you kind of look at the synaptic gaps in our brain, most mimic use the memristor as the equivalent to this. So where you have the two neuron ends, and that's kind of equivalent to our metals, and the synaptic gap is equivalent to the oxide layer, which is present between them. We've demonstrated resistive memory. We've demonstrated analog memory capabilities using these materials, nano devices, which is the application. In this particular case, we wanted to use this as the brain mimicking device, electronic skin type application. So this, in a snapshot, is what demonstrated. So if you look at our skin is always sensing all kinds of stimuli. You're sensing the changes in pressure. You're also sensing changes in temperature. And you're also sensing, but you don't react to every single thing. You react only when the temperature or the pressure being applied on our body exceeds a particular threshold. Now that threshold is kind of determined by your brain. So every time your skin is sensing something, that information is sent fantastically through electrical impulses through the nervous system to the brain. The brain then decides whether this is worth reacting to, and then it sends your information back into the nervous system. So if you think about it, like you're touching something extremely hot, that entire measuring, the information passing happens really, really quickly within a matter of seconds, and your brain sends the information to your hand to step away from that hot object, or just remove yourself from the hot object. So what we kind of demonstrated was kind of that. So we have the pressure sensing and the temperature sensing components, and we have the brain mimicking components, which is your memristor, and we kind of put these two together to mimic the entire skin concept. So the first thing which we demonstrated was a Pacinian corpuscle. Now this is the biological term, but essentially what it does is measure pressure. So if you look at all your fingers, you'll actually see that is the most obvious Pacinian corpuscle, which you can see on your skin. It's essentially sensing for pressure all the time. So having a pressure sensor connected up to a brain mimicking electronics, so having the strontium titanate based memristor sitting along with it kind of allowed us to mimic this pressure sensing aspects of it. So it's again extremely it's electronically driven. So the high resistance states or the low resistance states of the pressure sensor, depending on whether it's seeing pressure or not seeing pressure, drives the memristor between those two states, and that kind of decides the responses that the body generates. A very similar concept for thermoreceptors. So this is where our body is actually reacting to external temperatures. So we use the vanadium dioxide in this case to actually as a thermoreceptor in this particular case. So the fact that vanadium dioxide actually changes its electronic characteristics on heat, that is what we use to demonstrate the thermoreceptor characteristics. So again, we connected up the vanadium dioxide thermoreceptors with the brain mimicking strontium titanate memristors, and that the two circuits kind of drove each other depending on the external stimulus. So what you see in this case is the metal insulator transition usually happens at around 68 degrees centigrade. So while your body does not react for the initial temperatures, once the temperature exceeds a particular limit, it starts reacting to it. And based on how we configure the entire electrical system, the heat being applied on the thermoreceptor changes the resistance states of vanadium dioxide, which in turn changes the resistance states of the memory. The fascinating last concept in the electronic skin was the demonstration of the nociceptor concept. Now, this is basically where you're trying to demonstrate that our skin doesn't react to every single stimuli. It only reacts to stimuli once it exceeds a particular threshold. But if you see there are people who have a lot of skin conditions which makes them extra sensitive or hypersensitive to external stimuli. So these are allodynia and hyperalgesia. Now, allodynia is where even below stimuli which you normally respond to, a person starts reacting very, very strongly to the stimuli. For instance, say your skin is sunburnt, then you react very differently to, the presence of stimuli. Or hyperalgesia is where you have a very strong response. So even a tiny amount of pain, which most people are able to endure, is unbearable for people who usually have hyperalgesia. So using the vanadium dioxide with the strontium titanate kind of allows us to demonstrate these kind of damage states in our skin as well, because you're able to control the threshold at which the skin starts reacting to particular stimuli. This work which we did last year, so it's quite fascinating because pain sensing skin. So imagine adding this onto prosthetics. It really, really is fascinating because prosthetics currently do not have the ability to sense pain or to sense things the way normal skin senses it, or they're mainly being used to pick up things. So they've significantly enhanced people's life, but they're not as close to a real limb as they can be. So the addition of this kind of a skin-like layer, which is capable of sensing pain, the prosthetic can really, really significantly enhance the behavior or the feel of the entire, prosthetic arm. There are other possible applications for this work as well, be it in the form of or for defense applications to enhance the sensitivity which one might feel, or for smart glove applications where you again enhance the sensitivity which you might have in your hand, even though you're wearing a glove. So fascinating applications for that particular work. I'll move on to the last part of my presentation now, which is essentially talking about collaborations which go from lab to the market. So a lot of our work, as I mentioned, we are engineers, we are a big group of engineers. So for us, our main work has always been how do we make sure that we create technology which hopefully we can work quite closely with industry and then get it out into the market. It took us a long time to get here. As I indicated earlier, we had a lot of initial conversations which didn't quite go down that well. But then once we started having some really good turns in terms of talking to the right people, we've had a lot of success in the last couple of years. So now we work with 8 different industry partners to take our technology out into market for various applications. A lot of it is in the healthcare space. Some of it is in the aged care space as well. But one thing which we've realized as a result of this is for us to effectively take our work into the market, the collaboration is definitely key. So we see ourselves very much as a part of the collaborative network where we work quite closely with industry partners who, kind of identify the problem for us to work on, manufacturing partners, because, ultimately we're not going to generate a business and generate hundreds of prototypes from our labs. It needs to be mass manufacturable outside in the manufacturing capability facility. So how do we make sure that whatever we produce is actually manufacturable in large numbers? User-centric design, which is actually a very, very critical thing, which a lot of people generally don't usually do, but we've kind of incorporated this the last few years and found it immensely useful. So I think as engineers and scientists, sometimes we just look at it as does the sensor work or does not work? But when a product has to hit the market, it has to be appealing. It has to be something which anybody can pick up and use with ease without having to go through a complicated manual to understand how to use the product. And it has to be something which every age group can come back and use again and again. So having that user-centric design as a part of the entire collaboration has been really, really key for us to make sure that we develop technologies which are user-friendly. I'll just talk a little bit about our few industry partnered projects. So the first one is we have a partnership with a company called Nutromics. Now, this is fascinating. This is something which we've been working on for the last 1 year. And the idea for them was trying to create patches which stick on the skin. So you can see this lady here wearing a patch. And that patch essentially has an array of microneedles. And what those microneedles are essentially doing is they are kind of interrogating your interstitial fluid, which is present just below your skin surface. Now, interstitial fluid is kind of similar to saliva and to sweat in the sense they also have a lot of biomarker information about the body. So you don't need a blood test. Sometimes the interstitial fluid almost kind of has the same biomarkers which the blood has. And if you can pick up those in the interstitial fluid constantly, you get information about your body. So this patch allows you to sense those biomarkers continuously, and hopefully that allows you to get a better understanding about yourself. So their first imaginative idea in this case was there are a lot of people who are pre-diabetic. So there are people who are at the risk of developing diabetes, where simple changes which you make in your diet will actually allow you to control or not diabetes. So it's kind of being initially being pitched as a personalized diet tool. So imagine you're wearing a patch, you're eating something, and every time you eat something, you're kind of understanding how your glucose levels in your body is changed as a result of what you're eating. So having that personalized diet approach is the idea behind this entire patch. So we work quite closely with them in integrating the technology, miniaturizing the electronics for this entire thing, and as well as working quite closely with the manufacturing partner to understand how we can create thousands or hundreds of thousands of these prototypes. This is one of those collaborations where we also have the design partner working quite closely. So she comes along. So Dr. Leah Heiss, who is also at RMIT University, does a lot of the design work for which we do in collaboration. So she allows us to imagine what the technology is going to look like when somebody is actually practically using this. So what are those various layers which are there in the patch? So you have the microneedle array. How is the patch going to look? How is it actually going to feel? How are you going to apply the patch and make sure that it stays over there? And then how is the person actually going to get that information? So what's the app going to look like? And how is the person going to interact with that technology? The other thing which Leah also does really well is she develops user design journeys. So she kind of allows us to imagine how this, and this is particularly interesting or very critical for companies and industries to understand, because you're trying to understand who is this product to. So is this a product which is going to be available in the supermarket, or is this a product which the doctor is going to recommend to you and you're going to go and use it? So, this is again a simple example which, Leah comes up with, which kind of tells you where is this product going to actually be sold to the person, and then how is the person going to use it, and then how is the person going to understand better about themselves by using this patch. Fascinating work, and just understanding things from their concept and looking at it from their perspective really, really helps, because we understand that everybody interacts with technology very differently. A 20-year-old interacts with it very differently to a 65-year-old. So, how do you make sure that whatever technology you put out there is usable by no matter what the age group of the person is? This is again a patch which we developed for a company called Lepis. Now, this is mainly being developed for the aged care sector. So the idea here was there are a lot of residents who are in residential aged care facilities here in Australia. Quite a few of them also have dementia. So, and therefore they need to have the constant monitoring of skin temperature, or, to understand the early onset of infection. So, or similarly, you need to understand their oxygen levels, you need to understand the ECG or their heart rate. But instead of hooking them up to wires all day, how do you make sure that you can put a patch on them and just get that information off them through a mobile phone? So imagine someone wears a patch like this on their neck, and it doesn't really intrude with their day-to-day activities, and the nurse can just go and use a mobile phone on this and get the information in terms of skin temperature or oxygen levels or their ECG throughout the day, many times during the day, so that you can give them, the right kind of advice or the right kind of treatment at the right time. But you allow them to carry on with their lives without being hooked up to a lot of wires. So that's the kind of work which we do with Lepis. Once again, a lot of work on the sensor development and the wireless electronics aspects of it. A bunch of other industry partnering which we do is this is related to the biomarker sensors, which I presented earlier in the presentation. So using the antigen antibody approach, we've realized it's actually quite a versatile platform. So you can use it for a variety of biomarkers. You can use it for cancer detection. You can also use it for COVID-19 detection. So we work with quite a few medical institutes. So Peter Mac in this case, particularly for cancer detection, or for with company called Sotirius, which is for early onset of COVID-19 detection or for flu virus detection, to see if we can actually develop these miniature sensors to allow you to, track any biomarker or track any presence of virus or bacteria quite early. And the final example for industry partner project is this one, which is, in fact, our very first industry partnership was with this company called Sleeptight. Now, it's quite different in the sense we're not talking about putting patches on the skin or putting sensors in your hand. We are actually talking about integrating sensors within an entire mattress. So the idea behind this was trying to see if you can integrate sensors within fabric, having them integrated on a mattress, which sits in residential aged care facilities, which allows you to do overnight monitoring of the residents in the aged care facilities. So essentially, you must understand, is the person there in bed or not there in bed? Are they at the risk of falling out of bed? Is their health okay in bed? Can you actually determine if there are changes in the breathing rate or changes in the heart rate during the night? We also worked with a bedding manufacturer in this case, which was Sleep Easy. And that was fascinating because for 3 years, we had to ditch almost all our previous materials and our previous choices. And we had to work with them to make sure we can actually deliver a sensor and deliver a technique which can be mass manufactured. So working with them to recreate the entire sensor design, recreate the choice of materials, and make it mass manufacturable was our key for the last 3 years. It's at a really interesting phase right now, this particular project. So just a couple of weeks back, we actually launched the product. That's a product name. It's called Remy. And what you see over here is essentially what you get. So sensors which are integrated in covers, which allows you to do the overnight monitoring of a person's presence in bed in an aged care facility. We're going into field in a couple of months, and that should be an interesting phase to allow us to understand if this product really will allow us to support the aged care facilities as they need to be supported. So what we imagine is having these sensors within mattresses in various rooms in the aged care facility, and the nurse is able to have a dashboard of these where she's able to see, is the person in bed or not in bed? Are they at the very edge? Are they going to fall out? have they left to go and use the restroom and they've not come back, and so they need to go and check on them and things like that. Yep. So pretty exciting phase for Remy to be in, and that is been almost a 3 to 4 year journey to actually work quite closely with Sleep Tight and Sleep Easy to get there. I'll kind of summarize at this point, and I know this is a quirky summary slide and it's not as technical, but it's kind of allowed us to, this kind of captures everything which we do, in the sense we work as a group. Our group has grown quite immensely from a group of 2 in 2010. We've now grown to a group of nearly 35 to 40 people in 2021. We work on quite a few different fields, and for us, working on those different fields, collaborating with each other, collaborating not just with engineers, but collaborating with industry and with design partners as well, collaborating with the manufacturing partners as well, has allowed us to, demonstrate a lot of innovation, which we might not have been able to do otherwise. For us, diversity is something which we're very, very passionate about. So making sure we have a diverse team, that we work well with each other, and we bring all our personalities and all our creativity in to actually generate these outcomes has been something which is really interesting and that important to all of us. That's the team. That team photo was actually taken in 2019 before the pandemic. We had a recent get together a couple of weeks back when we finally could actually see each other face to face after a really long time. So it was really nice to do that. But that team has actually grown by another 10, 15 members in the last year or so. Thank you to all the various funding partners, the Australian Research Council, as well as the other funding partners who fund our various industry collaborations. And thank you again for listening to me for the last nearly 45 minutes. Thank you.
Thank you, Madhu, for the excellent talk. I'd request people to raise their hands, for questions. Yes, Karun.
Yes, thanks for the nice talk. I had a couple of questions on the PDMS what you talked about. So what kind of surface roughness or surface quality is required for the meta surface and the diffraction grating type applications? And then do you have to prepare the PDMS so that it's elastic enough that the results will be reproducible?
So we used exactly the same transfer process as we did earlier. So when you looked at the surface roughness, which we had for our zinc oxide, that was like around 160 nanometers. It's pretty much the same thing for the titanium dioxide, which we had for the meta surfaces. The fact that the titanium dioxide is not occupying such a large area, that it's nano disc, kind of reduces the surface roughness of the entire device a bit. But there was nothing really special being done to the PDMS to actually make it work for the meta surface application, as opposed to, making it work for the other applications. We had to work on the titanium dioxide a lot. We had to make sure that we had to get the annealing conditions right. I think we needed it to be anatase and not rutile. So making sure the titanium dioxide has the right property was more important than getting the PDMS to be the right properties, if that makes sense. And we haven't really fiddled a lot with the PDMS conditions. It's always been used in the same 1:10 ratio. And it's usable so it's not like an ultra stretchable PDMS or anything of that sort. It's just a standard PDMS, which you normally use for, say, like microfluidic type applications.
Okay, thank you.
Yeah, I have a couple of questions. So one is, in your slide number 13, if you please go back there. So you were talking about this effect of strain. Yeah, one more. Yeah, that's good. So, so it breaks and it stops responding, and then you leave it, and so it sort of comes back and it starts responding again. And how repeatable this process is in terms of, let's say, the resistance values and all?
So initially, after a point, say after 50 cycles or so it goes up towards open circuit. So initially, for the first, say, 15 or 20 cycles, it was really good, but then started increasing up slowly. But then with time, we have realized that if the oxide is fine and you work within a particular regime, you're able to get very repeatable resistance values. So you can go, we don't really push it in terms of number of cycles, maybe max 100, 200 cycles. but it's quite repeatable within that. So I think for a memristor devices, some of them may push them to up to around 300 or 400 cycles. And as long as we stay within the regime of the right amount of strain and not push it to the point where it's completely gone open circuit, you're able to get quite repeatable performance across those 500 cycles or so.
I see. Yeah. And another one is related to your slide number 16.
Yep.
So yeah. So was there any wavelength response with strain? Like, was the band gap changing in the zinc oxide?
Interesting question. We didn't really test it in this particular case because we only applied around 5% of strain. So the other thing which is fascinating with these materials is the more you micro or nano pattern it, the more strain you can apply on them. So with the zinc oxide work, these are quite large area devices. So you have kind of a thin film sitting everywhere, which means you can't really go beyond, say, 5 or 6%. If you micro pattern it, you can go up to around 15%. If you nano pattern it, you can go up to around 25% of strain. But that's a really interesting question in terms of, whether the strain is impacting the band gap of the material. That's kind of what we're trying to do to study our 2D materials. We're trying to understand if 2D material electronic characteristics kind of varying as a result of strain. We kind of doing that with the vanadium dioxide as well, trying to understand the insulator metal transition with the application of strain. But we didn't really look at the zinc oxide from that concept. But next time, we'll do that.
Yeah, because I would expect that your lattice constant is going to change. So something should happen.
It makes sense.
Another related question is, so did you check like the quality, the effect of the quality of the strain that you're applying, meaning uniaxial versus biaxial, and also compressive versus tensile?
With compressive and tensile, we did that for the titanium dioxides. For the gratings, we did go from -4% to around 18% of strain. But I think more often than not, it was uniaxial strain. And with some cases with our strontium titanate memristor work, we did a biaxial strain. But it's not something we have explored in great depth or detail.
Yeah, because I thought that this was more like a generic question related to flexible electronics. Like you don't know which way you are really stretching it, right? I mean, it could
True.
be a combination of biaxial and uniaxial in some sense.
True.
Yeah.
True.
Yeah. And another question, toward your later part of the talk, like I think slide number 14 or so. Well, I mean, what is the reason behind using STO? I mean, any specific reason?
So that strontium titanate, we started using it actually on a silicon platform. We didn't actually use it on a stretchable platform initially. But put simply, we started working on memristors back in 2016 or so, 2014 or so. And people had done a lot of work with titanium dioxide. But with sputtering, we found that we could actually control the number of oxygen vacancies in strontium titanate. And controlling oxygen vacancies is key for memristive devices. The other beauty which we discovered with strontium titanate was the fact that we could actually deposit at room temperature. So room temperature deposited strontium titanate for memristor behavior in our particular case. We could control the oxygen vacancies. We could dope the material with lanthanum or with chromium, I think, and niobium as well, and change the memristive characteristics. So I think we just hit upon strontium titanate because we could sputter it and control the oxygen vacancies, and also because it was not a very highly used material for memristor devices. But then it so happened that we found that it actually has quite nice properties, and the fact that it's room temperature deposited makes it quite advantageous for other applications.
I see. Yeah, because I thought it's significantly deviates from the commonly used materials like hafnia and alumina and all these. So was there any specific advantages? What I was trying to get at for STO?
So we had quite a few papers in 2015-16. We actually had a few patents as well in that space because until then, not many people had done strontium titanate memristors or had a room temperature deposited version of it. And doping gave us quite a lot of advantages. If we wanted to increase the endurance, we could dope it with one particular material. If you wanted to change the kind of switching behavior, we could dope it with another kind of material. So it was quite, sometimes I think we made the choice to stay away from other materials. I think a lot of work which we do in our group is kind of similar. Like when we say we work on 2D materials, people think we work on graphene, and we deliberately did not work on graphene or on molybdenum sulfide because we just wanted to use other materials and see if we could, progress on that particular front. So quite a lot of choices in the group are actually made that way.
Sure, I mean, very interesting. Yeah, and maybe the last question is, so in the same slide, I guess. So I thought you were using it as a pressure sensor or something. So did you actually use the piezoelectric property of STO, or no, you just? I mean, how did you actually sense the pressure?
No, so the STO was usually used as the brain mimicking electronics. So we usually use the STO membristors to kind of mimic the brain in the entire skin replicating device. The pressure sensor was a standard gold on PDMS pressure sensor. So it was just a gold pattern on PDMS, which was, being used to sense the pressure.
I see. Okay. Yeah, thank you. Is there any other question? Okay, I do not see any other raised hands. So thank you for the excellent talk. It was very interesting. I also particularly liked your industry collaborations. It's really something we all look for. And congratulations on your success on that.
Thank you. And I think that's the main thing I always try and make sure I tell everybody in my presentation, hang in there, you'll get there one day. So if you had spoken to me in 2016, 2017, 2018, there was no industry collaboration I could talk about, right? But I was talking to nearly 40, 50 different people at that point in time who were really interested in the work. But then things suddenly materialized in the last couple of years. So sometimes, it takes time. But I think finding the right partner is critically important, because if they don't value your research and respect your research, it makes it very difficult to work with them.
Sure. Yeah, great. All right then. Yep. Thank you everybody for attending. Yeah. Thanks, Madhu, again.
Thank you. Thank you for having me.
Yep.
See you.
Thank you. Bye all.